Good afternoon, everyone. My name is Bill Marari, and I'm presenting my confirmation of candidature for a doctorate in mechanical engineering. My research will be under the supervision of Professor Ji Yang and Dr. Henin Zhang. My thesis title is Dynamic Characteristics of Graphene-based Functionally Graded Composite Structures in Fluid. During this presentation, I'll introduce the significance of my research as well as its real-world application. I'll highlight some of the notable work that's been done so far. I'll point out some of the gaps in the literature, as well as the contribution the current research will have on the body of knowledge. I'll display the methodology that will be employed to address the gaps, as well as provide some concluding remarks. So a lot of real-world structures rely on a profound understanding of fluid structure interaction. Some of these structures include wind turbines, offshore structures, and deep underwater exploration structures. Specifically with offshore structures, these are structures that extract oil and gas, and their supports are situated in the seabed. They experience high dynamic loading, and it was determined that 96% of marine structure accidents were linked to operation, whereas only 4% were linked to the installation process. And improving their damping capabilities and stiffness would significantly reduce their risk of structural failure. And so this has led engineers to seek for solutions in composite structures. And one of these solutions is functionally graded materials. These are materials or structures whose mechanical properties, or whose properties in general, change smoothly and continuously along the thickness of the structure. They are lightweight and possess a high stiffness. For my research, I'll be looking at functionally graded materials reinforced with graphene. Some of the functionally graded materials you can have are those with a gradient in orientation, as well as a gradient in concentration. The ideal functionally graded material is one with a continuous sort of blend that you can see in the bottom left corner. However, this is both numerically and experimentally impossible to achieve. And so engineers have created a numerical approximation that's a layer-wise gradient, and this usually comes down to 10 to 15 layers. This is an ASTM tensile specimen that contains 6 layers, and it's a functionally graded graphene-reinforced composite sample. And as you can see from the gradation diagram, most of the graphene is in the top and bottom layers. This particular distribution pattern was observed to be favorable in effectively reducing, to provide effective vibration response and improving the damping capabilities. And it was also observed that functionally graded materials have some advantages over composite laminates. Some of these advantages include, since there's no sudden change in material properties, functionally graded materials do not have the interfacial debonding that composite laminates experience. Functionally graded materials are multifunctional and can meet different performance requirements all at the same time, and this makes them more applicable. And lastly, they are an effective solution to enhancing material properties while conserving weight. And what makes graphene so special is that within its rings, the carbon atoms are sp2 hybridized, which allows them to form carbon-to-carbon double bonds. And this is incredibly difficult to break, hence the really high Young's modulus of 2 terapascals. And it was also observed that functionally graded graphene-reinforced composites perform better than functionally graded carbon nanotube reinforced composites in terms of mechanical and thermal, as well as electrical properties. And this is because carbon nanotubes possess weak van der Waals forces between them, which cause poor load transfer, as well as slippage in the case of tensile loading. However, for graphene, it's got a lot of properties which work in its favor. Specifically, graphene has a large surface area which facilitates the bonding between graphene and the matrix. It has a wrinkled or rough surface, which facilitates the formation of mechanical interlocks at the nanofiller and matrix interface. It also has several structural defects which provide an opportunity for the formation of covalent bonds with the matrix. And so specifically, when it comes to functionally graded graphene-reinforced composite structures, graphene has all the aforementioned mechanical properties, which make it a highly sought-after reinforcement for polymers and metals. However, graphene reinforcement is highly dependent on how well it's dispersed within the matrix. Otherwise, you run into issues such as agglomeration. And in comparison to other carbon-based nanofillers, graphene has a large surface area. It's really cheap to manufacture, and it's highly effective in small quantities. And lastly, graphene can be functionalized to further improve its bonding with an epoxy matrix. So when it comes to the state of the art, one study aimed at determining how graphene reinforcement compares to that of carbon nanotube reinforcement. So we can see from the first figure that only a 0.1% addition of graphene into a pristine epoxy improves its tensile strength by 40% in comparison to 11% and 14% in the case of single-walled and multi-walled carbon nanotubes, respectively. The second image, we can see that there's a 31% increase in the Young's modulus for the graphene-reinforced pristine epoxy in comparison to the less than 3% of 3% improvement in the pristine epoxy reinforced with nanotubes. However, we can see a bit of an underprediction, which is caused by the assumption in the micromechanics models. This model assumes that the graphene structure is rectangular rather than waving, and so there's a bit of an underprediction in the surface area, which contributes to the load transfer. So another study aimed at determining the effect of different boundary conditions on the natural frequency of a functionally graded graphene reinforced composite beam. And so it makes sense that the graphene with the least reinforcement, with the least restrictions at the boundary condition, at the boundaries, would have the highest natural frequency. However, we can also see that this much improvement was only caused by a 0.5% increase, a 0.5% addition in graphene. We can also see that the pattern with the most graphene in the top and bottom layers is the most effective overall. And so another study, or the same study, looked at the effect of graphene weight fraction on the natural frequency of these types of beams. So specifically with pattern 3, again, we can see that only a 0.1% addition of graphene can cause about a 25% increase in the natural frequency. And adding a 0.5 can almost double your natural frequency. So another study looked at the effect of the graphene geometry on the natural frequency of functionally graded graphene reinforced beam in air. So we can see that for all distribution patterns, there's a general increase in the natural frequency up to a certain point. And this is because beyond this point, there's no significant improvement in the surface area. And so there's no significant load transfer that could cause a further dramatic change in the natural frequency. Another study looked at the effect of increasing the fluid density. So we can see that as the fluid density increases, there's an increasing reduction in the natural frequency, which denotes the effect of the hydrodynamic loading. The horizontal axis is G, which denotes the fluid immersion level, whereby G equals 0 denotes fluid air, whereas when G is 1, the beam is fully immersed. The same study also looks at the effect of the beam slenderness ratio, where we can see that the beam with the smallest slenderness ratio it depicts the highest influence of the hydrodynamic loading, and this is because on this beam there's not enough surface area for all the pressure to act, and so the effect is higher in comparison to the beams with higher slenderness ratios. And so with all this, I identified a few gaps which all stem from the lack of research on the free and forced vibration in functionally graded graphene reinforced beams submerged in a fluid. And so from this, we can also, the gaps I noticed were there's no research on the effect of the geometric properties of graphene, the effect of the fluid flow, the influence of the graphene distribution pattern, as well as the boundary conditions. So the research goals I'll be looking at will be oriented towards determining the dynamic behaviors of these beams submerged in a fluid. Specifically, I'll be analyzing the free and forced vibration, as well as the impact response of functionally graded beams, both in steady and laminar flows. And then the last goal will be aimed at analyzing the effect of a variable cross-section of a beam to its dynamic characteristics. And so the research questions I'll be pursuing are determining which distribution pattern is the most effective to result in vibration attenuation. Also be looking for the most effective GPL weight fraction in reducing vibration. Also be interested in how different boundary conditions affect the dynamic response of a graphene-based functionally graded beam. And lastly, I'll be looking at the effect of the fluid depth on the resulting natural frequencies. And in terms of the methodology I'll use to address the different questions, this is a bit of a summary. The first step will be to apply a shear deformation beam theory. This is very fundamental because it determines how the beam will deform. And the first beam theory I'll apply is the Timoshenko beam theory, in which the plane sections remain perpendicular after deformation. And so this leads to the introduction of the phi x term, which denotes the rotation of the plane section with respect to the vertical axis. It also introduces the shear correction factor, which accounts for the assumption that the shear stress remains constant throughout the thickness of the beam, which isn't the case. The other beam theory is the more accurate one, which uses a cubic polynomial to depict the plane section deformation. It also doesn't require the shear correction factor, as there's the transverse shear stress terms, which facilitate an accurate depiction of the transverse shear stress diagram. So from the aforementioned beam theories, we can then achieve all these displacement fields. So the second step is the micromechanics models, which are used to predict the effective macroscopic mechanical properties of the beam. They rely on the molecular dynamics simulations for verification. I'll be applying the modified Halpin-Tsai model, which takes into account both the geometric properties as well as the filler orientation. And so, as we've seen before in the state of the art, sometimes this model underpredicts the Young's modulus due to the shape assumption. The first expression is the original Halpin-Tsai model, and we can see that C term, which is used to depict the GPL or the graphene shape characteristics. The second expression is one type of modified Halpin-Tsai model, which takes into account the temperature considerations, and the G term, which takes into account the atomic vacancy considerations. And the last term contains the gamma term, which is used to depict the discrepancy between the numerical results and the molecular dynamic simulation. The third step is the fluid structure interaction which is used to depict the interaction at the fluid structure interface. And so this takes into account the hydrodynamic effect. And I also mentioned that I'll be interested in the effect of the fluid flow on the dynamic response of the beam, and this is taken into account in the velocity potential function. And the first numerical method I'll apply will be the Ritz method, which applies a series of generalized functions which satisfy a set of boundary conditions. So for instance, I'll be interested in the effect of different boundary conditions on the dynamic response of the beam. And so while applying the Ritz method, I'll have to determine a set of trial functions which meet the corresponding boundary conditions. And so in the expression you can see here, the trial function will be the phi term, and the c term will be the coefficients, which will then need to be determined by minimizing the total energy term. The second numerical method I'll be applying is the differential quadrature method, which approximates the partial derivatives in the governing equations as the sum of linear weighted function values. And so some weight coefficients are important parameters in this numerical procedure, and I'll be applying the Quan and Chang approach to determine the weight coefficients. And so the last step will be determining the natural frequency and the mode shapes. And so this is a summary of the algorithm that I'll apply. The first step is determining the eigenvalue and eigenvector of the beam by itself without taking into account the fluid immersion. And then the next step will then be to use the eigenvector from step 1 to determine the eigenmass matrix term, as well as the new eigenvalues and eigenvector. So this procedure is repeated until the relative error between two successive eigenvalues is in the range of 0.1%. And then from here, you can then construct several graphs based on the natural frequency. Other parameters I'll be interested in are the added mass and damping coefficients. And so putting the technical aspect aside, this is a brief description of the timeline. And so the literature review will be an ongoing process, and I plan on starting the thesis after the third milestone. The first 6 months of this research was spent collecting background knowledge, and then I began focusing on this research around August last year. And then the past 3 months was spent preparing for this conference in terms of this presentation as well as the research proposal. And then I've divided the remaining period I have in this PhD amongst the different objectives I have. And so I've allocated 6 months to each one, and I'll see how I go from there. In terms of concluding remarks, functionally graded materials are the solution to enhancing material properties while conserving weight. And not only does graphene provide exceptional reinforcing capabilities, but also only a small amount is required to exhibit significant improvement. Also, the dynamic behavior of functionally graded graphene reinforced beams in air is well researched. However, there's no research on these types of beams in the fluid environment while analyzing their behavior. And ultimately, this research will build on the body of knowledge by investigating the free and forced vibration as well as the impact response of functionally graded graphene reinforced beams submerged in a fluid while considering the fluid structure interaction. With that, I thank you for your time, and I'll be happy to take your questions.